So, in our last lecture we were talking about the various IO transfer techniques, specifically under the programmed IO category. So, if you recall, we looked at synchronous method of data transmission, then we looked at asynchronous or handshaking, and finally, we were discussing the concept of interrupt driven data transfer. So, in case of interrupt driven data transfer, what we saw was the processor is doing something. Whenever the IO device is ready or the IO module is ready to transfer some data, it will be interrupting the CPU by sending a interrupt request signal. The CPU, when it receives the interrupt request signal, will know that some IO device is now ready to transfer data. So, it will be jumping to some interrupt service routine ISR, where the data transfer will take place, and after that it will again return back to the program which it was executing. So, here while the device is getting ready for transfer, the CPU is able to do something else. CPU is not getting tied up. So, we shall be continuing our discussion on interrupt driven data transfer, in particularly the topic of interrupt handling. This we shall be discussing today. So, let us see, we mentioned this earlier also, that what exactly happens when an interrupt request reaches the CPU. Okay? Well, the first thing that happens typically is that the CPU was executing some instruction when the interrupt request came. So, typically we shall be seeing that some exceptions can be there. Typically, the instruction which was being executed will first complete, and only after that the interrupt request will be acknowledged. Okay? So, what we are saying is that at the end of the current instruction execution, so during the interrupt acknowledge cycle, what is done? The program counter and the program status word, or PSW it is sometimes called, they are saved in a stack. So, you may recall that for normal subroutine or function call and return, only the return address, that means the value of the program counter PC, that is saved in the stack. But here we are saving not only the PC, but also some status information. It of course depends on the processor, the ISA, what this PSW means or refers to. Okay. So, typically in computer systems where there are status flags, PSW will contain status flags and some other processor status information regarding which level of privilege it is working on, and so on and so forth. Now, you may recall in MIPS 32 processor we do not have any such status flags. So, saving of the PSW becomes much simpler there. Okay? Fine. So, after this is done, the interrupt is acknowledged, which means the interrupt acknowledge signal is activated, and means on acknowledging the signal, as I had mentioned, the external interrupting device or the IO module, it can supply the interrupt vector. The interrupt vector will identify the device who has interrupted. Using that information, you can compute the address of the interrupt service routine and transfer control to that. Okay. Now, of course, different devices may be having different service routines. So, you need to get the address of the correct service routine and then jump to that. Now, after the interrupt handling is completed, the interrupt service routine executes a return, but this is a special kind of a return instruction, not a normal return instruction that you do to return from a subroutine or a function, where only typically the program counter is popped from the stack and is loaded into PC, but here you have to restore not only the value of the PC, but also the program status word which was also saved. Okay. So, this is a special kind of instruction, let us say RTI. So, this will restore the PSW and return control to the saved PC address. So, as I said, this is slightly different from the normal return instruction, where PSW is not saved and returned, okay? Just only the PC is restored. Fine. Now, let us look at an instruction cycle now. Now, in a MIPS 32, you recall the instruction cycle consists of 5 steps: IF, ID, EX, MEM and WB. These are typically called machine cycles. So, an instruction cycle comprises of typically more than one machine cycles. So, these machine cycles are executed in order to complete the execution of an instruction. Now, let us see. So, it is at this point when the instruction cycle is complete, the instruction execution is complete, only then interrupts are acknowledged. But in between the machine cycles, interrupts are not acknowledged. Even if the interrupt may appear earlier, but the processor will wait till the instruction execution is complete, only then the interrupt system will get acknowledged. This is how it works, right. Now, in this context, you may recall one thing, that we talked about the machine cycles, instruction cycle and said that interrupts will be acknowledged only at the end of the instruction cycle, not in between. But there is another method of IO transfer which we have not discussed yet, that is direct memory access. So, if you recall, we mentioned earlier, DMA is one method using which the IO device can directly transfer some data to memory or back without intervention of the CPU. Okay. Now, here there is slightly difference in terms of the handling of the DMA requests. So, whenever a device wants to make such DMA transfer, we shall be seeing later that we can stop the processor not only at the end of the instruction cycle, but in between also. At the end of a machine cycle we can stop, at the end of IF we can stop, at the end of ID or EX or MEM we can stop. This is possible because while the transfer is going on, the CPU status is not changing, it is just like a pause. While the transfer is going on, CPU will pause and then it will again continue. This is one difference. Fine. Now, the general interrupt processing can be summarized by this flow diagram, where these blue part, the portion which is marked in blue, these are performed in the hardware unit in the CPU, while the pink part, this side, these are performed by software as part of the interrupt service routine. So, let us see what happens. The device controller to which the IO device is connected, it issues an interrupt request. So, CPU receives that, CPU will finish the execution of the current instruction as I had said, and only after that the CPU will save the PC and the PSW. Of course, it is after that it will acknowledge the interrupt and it will save PSW and PC in the stack. See, after acknowledging the interrupt, as I said, somehow the CPU will also know or try to know that which device has interrupted. So, there the interrupt vector concept can come in. So, whenever interrupt acknowledge is coming, the external device controller will be pushing some kind of a interrupt vector or a device ID on the data bus. CPU can read it and can identify the device. Now, depending on the device, CPU will be jumping to the appropriate interrupt service routine, which means it will loading the program counter with the address of the corresponding ISR. After this is done, control will jump to the interrupt service routine, it is here. Now, you see this part is done by the CPU automatically whenever the interrupt comes, but here when ISR is assumed control, there is a program code which is written, this is software. So, it will be saving some other processor information if required, maybe some registers it will be saving, and it will be processing the request. If it is a data transfer, it will be actually carrying out the transfer, and whatever registers for example were saved, it will restore them back and it will return back by restoring the old PSW and PC. So, the program was running. So, wherever the interrupt request came, the control would branch to the ISR. After ISR finishes, it will come back. Now, the point to note is that suppose this was a program which was executing, there were many instructions, and let us say this is my ISR. Now, you cannot predict beforehand exactly where the interrupt will come. Maybe the interrupt will arrive here. Then after the execution of this instruction, you will be jumping to the ISR, it will finish and then it will return back. Maybe the interrupt has come here, then after execution of this, control will jump, it will get executed and it will be returning here. So, it can actually jump from anywhere in the program depending on where the interrupt request is actually coming. Okay? Fine. So, this is a picture which shows the CPU, the device controller and the bus, the overall picture. So, exactly what we have said. The device controller will be sending an interrupt request to the CPU. CPU at the end of the current instruction execution will be sending back an interrupt acknowledge. So, in response to that, device controller will be pushing an interrupt vector on the data bus, CPU will be reading that interrupt vector and will be able to identify which device has interrupted, right. So, the steps are as follows. As I said, device controller sends interrupt request to the CPU, CPU finishes the current instruction and sends back acknowledgement, device controller sends interrupt vector number on the data bus, CPU will read it and identify the device. This is exactly what I have said with respect to this diagram, right. Fine. Now, the question is, how is the interrupt vector sent to the data bus in response to INTA? Whatever we have said, that whenever this INTA signal is coming, the device will be putting the interrupt vector on the data bus, but how does it happen automatically? Okay, it is very simple. Here actually what we require here is a tri-state buffer. So, on the input side of the tri-state buffer, we have the interrupt vector, the output of which is connected to the data bus, and the tri-state buffer is enabled by the interrupt acknowledgement signal. Now, you recall what is a tri-state buffer? A tri-state buffer is a circuit which has an enable. Suppose I have an input A and the output B. So, if this buffer is enabled, then B will be equal to A. If the enable, suppose enable B equal to A, if enable equal to 1, let us say, but if it is not enabled, then the output will be electrically disconnected. We call it, it will be in the high impedance state if enable is 0. So, this tri-state buffer can either connect or disconnect a signal from a destination point. In this case, the destination point is the data bus. Okay. So, whenever interrupt acknowledge is active, the interrupt vector will appear on the data bus. So, when it is not active, tri-state buffer will be making the output lines high impedance state. So, as if this is not there, the data bus will work as it is. So, this is what I said, this gets activated when INTA is active, and the interrupt vector which is pushed on the data bus, this can be read by the CPU. This will help the CPU to identify which device had interrupted, and accordingly it can identify the correct interrupt service routine. right. Okay. Now, let us consider the scenario where multiple devices can interrupt the CPU. So, let us look at a scenario like this. I will look into the detail of this block later. Suppose there are several devices connected on this side. Now, each of these devices will be having an interrupt request and interrupt acknowledge. Let us say there are 4 sets: interrupt request 0, interrupt acknowledge 0, then interrupt request 1, interrupt acknowledge 1, then 2, interrupt request acknowledge, and 3. There are 4 in this example. Now, when there are multiple devices that needs to interrupt the CPU, so one common solution is to have a device which is called a priority interrupt controller. So, priority interrupt controller works just exactly like is shown in this diagram. So, on one side it will be having multiple sets of interrupt request and acknowledge lines through which various device controllers can be connected, but on the side of the CPU there is a single interrupt line and a single interrupt acknowledge line. So, this is exactly what is written here. The interrupt controller interacts with CPU on one side and multiple devices on the other side. Now, here the idea is whenever any one of the devices will be sending an interrupt request, the priority interrupt controller will automatically generate an interrupt request to the CPU, and when the CPU sends back the acknowledgement, the interrupt controller knows that which device had sent the interrupt. So, whenever acknowledgement comes, this interrupt controller will be putting the appropriate interrupt vector on the data bus corresponding to that interrupting device. So, interrupt controller is responsible for sending the correct interrupt vector to the CPU. But just one thing, if suppose 2 or more interrupt lines are activated simultaneously, then what will happen? Then this priority comes into the picture. Well, let us say you define a priority where this line 0 has higher priority than 1, 1 has higher priority than 2, and 2 has higher priority than 3. So, if interrupt request 0 and interrupt request 2 they are activated simultaneously, then this interrupt request 0 will be processed and 2 will be ignored for the time being. So, later on, so after finishing the processing of interrupt request 0, then if the interrupt request 2 is still active, it will be processed and handled. This is a typical way using which multiple interrupts, simultaneously coming interrupts, can be handled. Right. So, how it works? The interrupt line, as I said, is activated when some of the devices activate their interrupt request line. So, how it can be implemented? Just logical OR. You use a simple OR gate, a 4 input OR gate, where the 4 interrupt request lines are connected to the 4 inputs, and the output will be generating the consolidated interrupt request signal to the CPU. This is how this is generated, a simple OR function. Okay. This is one. Then the CPU sends back, okay, this should be interrupt acknowledge, INTA. So, when the CPU sends back INTA, the interrupt controller will send back the corresponding acknowledge to the interrupting device and puts the interrupt vector on the data bus. What is I mean here is this: suppose I have the priority interrupt controller here, this is PIC, and let us suppose device number 2 had interrupted, INTR 2. So, in response by this OR function, the CPU got this INTR. So, later on when the CPU generates the acknowledgement, the PIC will be generating the corresponding acknowledgement for this device 2, INTA 2. This will be done automatically, right. And it also has another responsibility, it is also connected to the data bus. So, whenever this interrupt acknowledge is sent by the CPU, so the corresponding interrupt vector, because PIC also stores the different values of the interrupt vector for all the devices. So, the interrupt vector for this particular device will be pushed on the data bus, so that the CPU can read the value and know that which of the 4 devices had actually interrupted, right, fine. So, this is the second step, and the third point to note is that, as I said, that the interrupt controller can be storing the interrupt vectors for the different devices. So, the interrupt controller is in some sense programmable. Programmable means before you are using it, you can specify that these will be the interrupt vectors for the 4 devices. The CPU can initialize some internal register within that PIC, where the values of the interrupt vectors can be programmed or specified. Okay? Fine. And as it said just previously, so if more than one requests are activated simultaneously, we can use a priority mechanism. So, let us say by convention interrupt 0 can be having the highest priority, followed by interrupt 1, followed by interrupt 2, and then interrupt 3. Okay. Fine. Another issue is nesting of interrupts. Let us consider a scenario. Let us say a device D0 had sent an interrupt to the CPU, and the CPU is currently executing the corresponding ISR. Now, while this ISR is being executed, let us assume that another device D1 has interrupted. So, what I am saying is that some program was executing, this was a program it was executing, in between there was an interrupt, this interrupt was by device D0. So, because of this interrupt, the control had transferred to the ISR corresponding to device D0, there are instructions. So, it is being executed. So, after finishing it is supposed to come back like this and resume execution, but what we are assuming is that while this ISR D0 was executing, in between there is another interrupt which has arrived from device 1. So, now you may argue that well, there is also an ISR for device D1 that also consists of instruction. So, should we stop this, go here, process this and then come back and resume here? This is called nesting, that before something is finished you are going to somewhere else. This is nesting of interrupt requests. Before the handling of interrupt request D0 is finished, another interrupt has come. Okay? This is what is meant by nesting. So, for nesting there can be 2 possible scenarios you can think of how to handle this. Well, the first one is what I have just now illustrated. D1 can interrupt the interrupt service routine for D0, get processed first, and then the ISR of D0 will be resumed, just like what I showed here. So, when the D1 interrupt comes, the ISR of D1 will be processed first, then it will come back and ISR of D0 will be resumed and then it will be finished. Okay. Now, this will involve nesting of interrupts and theoretically means any arbitrary number of such nestings can happen, because interrupts may appear one after the other. So, some important interrupt request which came earlier might get delayed for its processing. So, the other thing is that you can disable the interrupt system automatically whenever an interrupt is acknowledged, so that handling of nested interrupts is not required, because if you disable the interrupt system, then if some interrupt request comes, it will not be considered, it will be ignored. This is another solution. So, whenever you are processing an interrupt service routine, you disable the interrupt system, so that it will not be disturbed by some other interrupts. Okay, so, nesting will not happen. Okay. So, for this, typical machine instructions are there for enabling and disabling interrupts like EI and DI, something like this. So, for this second scenario, the interrupt service routine will give an enable interrupt instruction just before return from interrupt. So, you see what is happening. Now, we are having a design where whenever an interrupt comes, before jumping to the ISR, interrupt is disabled. Like what I am saying is that a program was executing, an interrupt comes, interrupt request. So, before you are jumping to the ISR, let us say this is your ISR. Before you are jumping to the ISR, you are means the hardware is automatically disabling the interrupt, so that execution of the ISR will not be interrupted. And in the ISR, what is happening, before the return from interrupt instruction, that is supposed to be the last instruction, there will be an explicit enable interrupt instruction. So, that before returning back, you are enabling interrupt again, so that any future interrupt, if it comes, it should be acknowledged. Okay. So, some instruction set architecture, they combine EI and RTI in a single instruction. So, when you do a return from means return from interrupt, so interrupt will be automatically enabled, you do not need a separate EI. And the DI instruction can be used for some other purposes also, like sometimes the operating system can execute DI to prevent interrupts from coming. Like there are parts of the operating system where some atomic code is executed. Some example is semaphore wait and signal operations. For those who have studied operating systems, you will know. Means atomic means there is a function which you should either execute completely or should not execute at all. It should never happen that we execute the code halfway through, then an interrupt comes and you have to stop. It should not be allowed like that. So, to allow atomic code execution, this interrupt system can be disabled. Okay. So, no external device or anyone should interrupt the code while it is being executed. For that, DI instruction can be used. So, with this you see, we have seen the different cases of interrupts. There are some cases which can make the interrupt handling more difficult. Like we have assumed so far that whenever an interrupt is coming, I have to finish the current instruction, then only I can acknowledge the interrupt. But there are some cases, examples where you cannot finish the current instruction, that makes interrupt handling more difficult. So, this is what is mentioned here. For some kinds of interrupt, it is not possible to finish the execution of the current instruction. So, for such cases you need a special return instruction that would be returning from the ISR, but after returning it will be restarting the same instruction which was interrupted, not that it will be returning to the next instruction. It will be restarting the interrupted instruction. Some examples are page fault. This happens in operating system in the memory management. When a memory location is accessed which is not presently loaded in memory, a page fault interrupt comes. So, you will have to load the requested memory location, the page in memory, come back and again restart the instruction, so that it can access the memory location correctly this time. Okay. And you can also think of arithmetic exceptions like division by 0, square root of a negative number. So, in such cases you are not able to finish the instruction. So, interrupt handling has to start before the completion of the instruction. So, such cases can make interrupt handling more difficult. So, with this we come to the end of this lecture. In the next lecture also we shall be continuing with our discussion on interrupts, and we shall see some more issues, particularly regarding multiple devices sending interrupts and the different types of interrupts and so on. Thank you.